Thank you for the introduction, and thank you for the opportunity to speak here. My research is surrounds arithmetic statistics of elliptic curves. So one kind of quantity that I was looking at is Szpiro ratio. So first, well, I guess we should define what the Szpiro ratio is. The Szpiro ratio depends on the minimal discriminant of the elliptic curve and the conductor. So let's maybe just go through some of the definitions. So if we take an elliptic curve defined over the rationals, we study the Q isomorphism classes of elliptic curves. Then there is a global minimal model. So it will be kind of a model of this form chosen in such a way such that the discriminant is minimal, and the minimal discriminant is a polynomial in terms of these coefficients, A1 to A6. The discriminant usually depends on the model, but well, since there's a unique global minimal model, this minimal discriminant is the kind of unique quantity that is kind of smaller, as small as possible over all models of this elliptic curve. Just kind of for the purpose of this talk and just in general if we want to kind of reduce the number of variables here, because here there are the 5 coefficients A1 to A6, which is quite a lot to handle, but we can restrict ourselves to minimal short fast model. So we can take a model where essentially we're taking A1 to A3 being 0, but then we're keeping A4 and A6. And there's across all such models, there's a minimal 1. We can kind of more easily describe what this minimal model is. It's the A and B are chosen such that any 4th power dividing A, its 6th power should not divide B. And there's a way to kind of uniquely transform the model to the minimal one. And the discriminant of this minimal Schwarzschild model is just some factors of 2 and factors of 3 times the minimal discriminant of the curve. So if we just be sloppy, we can just be a bit, if we don't care about the factors at 2 and 3, it just be a little bit sloppy. And kind of for simplicity of this talk, I will just kind of think of the minimal discriminant as something that is related to kind of this polynomial here in terms of just A and B. It will turn out that the factors in 2 and 3 do not really matter so much in what I'm going to study. And it's just cleaner to just kind of think of it as just a polynomial in 2 variables instead of having to deal with all 5. So that's a discriminant or the minimal discriminant of the elliptic curve. So next, let me just review some facts about the conductor. So the conductor of elliptic curve now does not depend on the model of the curve. It encodes the reduction type of the elliptic curve at different primes. So it's a product of primes at where this curve has bad reduction. The exponents here depends on the reduction type. So it's 0 if it's good reduction. So if there's good reduction, this prime does not occur in the conductor. If there's multiplicative reduction, this prime will occur with multiplicity 1. And if it's additive reduction, it will be multiplicity 2 in the conductor, at least for primes that are not 2 and 3. And for 2 and 3, there are more cases which I'll not list here. But for primes that are, for most primes, this is what kind of defines the exponent in the conductor. And in particular, so for almost all primes, this elliptic curve would have good reduction. But over places over primes where there is a bad reduction, usually it will be multiplicative reduction, because additive reduction occurs when P divides A and P divides B at the same time. And you can just very roughly speaking, the probability of this happening is like 1 over P squared. So for most primes, for when the prime is large, this probability is kind of small. So we expect kind of, if we just pick a random prime that's a bad reduction, then usually it should be a multiplicative reduction. Okay, so that's the conductor, and given the integral model of an elliptic curve, we can compute the minimal discriminant and the conductor using Tate's algorithm. So given an integral model, there's kind of an algorithm, and it's usually not too hard to compute what the discriminant and the conductors are. And the prime factors of the minimal discriminant are precisely the primes where the elliptic curve has bad reduction, which is also precisely the primes that occurs in the conductor. So the primes that divides the conductor are exactly the same set as the primes that divides the minimal discriminant. And there's also Oak's formula, which implies that the exponent of any prime that divides the minimal discriminant is larger than the exponent in the conductor. So in particular, the conductor would divide the minimal discriminant, and so I guess also in particular, the conductor is less than has to be less than the absolute value of the minimal discriminant. But it is possible that there is some prime that divides the minimal discriminant to some large exponent, but divides only the conductor some small exponent. So, right, but yeah. So Szpiro's conjecture. So Szpiro's conjecture tells us that I guess this doesn't happen. Well, this shouldn't happen very often. So Szpiro's conjecture says that the minimal discriminant should be bounded above by some constant times the conductor to 6 plus epsilon for all elliptic curves. So in some sense, the this exponent here is telling you that well, kind of logarithmically, the minimal discriminant shouldn't be too large compared to the conductor. And since we are kind of interested in kind of this logarithmic exponent, this exponent here, it makes sense to take logs and think about what's called the Szpiro ratio. So instead of so we'll try to kind of translate this. We can try to translate this inequality to something that is about the exponent by defining the Szpiro ratio as the log of the minimal discriminant over log of the conductor. So with this Szpiro ratio definition, an alternative way of kind of formulating Szpiro's conjecture is by saying that this Szpiro ratio is bounded above by 6 plus epsilon for all elliptic curves except finitely many exceptions. So just in the previous slide, because from Oak's formula we have that the minimal discriminant is greater than the conductor. So trivially, the Szpiro ratio is at least 1. So this gives the lower bound for the Szpiro ratio is kind of trivial, but so what we don't have is a uniform upper bound on the Szpiro ratio, but the conjecture is that this should be almost always bounded by 6 plus epsilon. All right, so this is Szpiro's conjecture. There's a closely related conjecture. There's a conjecture that is closely related to Szpiro's conjecture, which is the ABC conjecture. The ABC conjecture says that, well, given an ABC triple, which is 3 non-zero integers A, B, and C that are co-prime and that satisfy A plus B equals to C, then ABC conjecture says that they should satisfy the maximum of the absolute value of A, B, and C should be bounded by some constant times the radical of A, B, C to 1 plus epsilon, where I'm writing the radical as rad of n to mean the product of distinct primes that divides the integer n. Just by kind of comparing the two inequalities that's in the Szpiro ratio and ABC conjecture, you can kind of see they're both kind of telling you something about the multiplicity of, well, like the multiplicity of the essentially of the prime divisors. It's saying that kind of for most primes you shouldn't that appears in I guess this quantity on the left hand side, it shouldn't appear with a high high multiplicity because it's bounded by just a bit more than the products of prime that divides it. As I kind of briefly mentioned before, the conductor is a product of bad primes, and usually these primes should have bad reduction. So should have multiplicative reduction. So the conductor is usually in some vague sense very square free in some sense. So this conductor is in some vague sense very, very closely related to, I guess, the radical of the discriminant. So just to put it a little bit more formally, the Szpiro's conjecture implies a weak version of the ABC conjecture. By weak, I mean that you replace the exponent 1 in the inequality to something a little bit bigger. So there is some explicit construction. You could, well, given an ABC triple, so A plus B equals to C with ABC co-prime, we can just construct an elliptic curve using the A and the B's, and then computing the minimal discriminant and the conductor of this family of elliptic curves. You see that the discriminant has the form A times B times A plus B in the an all to square, and this A plus B, since we are since we have an ABC triple, this A plus B is precisely the C that comes from the triple, and also in the and then the conductor here is precisely AB, up to a factor of some factor of 2, the radical of A times B times C. And there are no primes that divides the conductor with higher exponent other than possibly 2, because A and B here are co-prime. So there's no, other than maybe 2 or 3, A and B, any prime that's of bad reduction cannot divide both A and B. So the conductor is just simply up to this constant, just the radical of A, B, and C. So then just by doing this more carefully and checking what you get from the application of Spiro's conjecture on these two quantities, then you'll be able to conclude that the maximum of A, B, and C is bounded by some the radical of A, B, C to some exponent. So that's just a very sketchy version of kind of one of this implication. You can also do it the other way around. It's known that the ABC conjecture implies Spiro's conjecture. And again, there's some explicit construction that you could do. So given an elliptic curve in its short Weierstrass model, this is just a discriminant formula that I've stated at the beginning. After removing any GCD of A and B in some after clearing the GCD of A and B in some way, you kind of want to impose that this is A and this is B and this whole thing is C in your ABC triple. So this is after removing any GCD appropriately. Then you can apply applying ABC conjecture on this triple. On this triple would give you the Spiro's conjecture. Right. So this just shows you that the Spiro's conjecture and the ABC conjecture are very related. Yes, and next I want to right, and the next thing I want to do is to kind of show you that just again a very sketchy construction to show you that the exponent 6 cannot be lowered in Spiro's conjecture. So there's a reason why you have a 6 in the exponent. So kind of a way to construct this is say take a rank 1 curve, a rank 1 model curve, which for example y squared equals x cubed plus 2 is a rank 1 elliptic curve. You can take any rational points that's non-torsion, any rational point there's no torsion, so any rational point on them, and you can kind of express the rational points in this form. Then the A, B, and C would satisfy this equation here just by kind of rescaling plugging in and rescaling the coefficient. So you get kind of infinitely many solutions to this this curve here. Then you can construct some elliptic curves using these coefficients. And because of how we've constructed how we've constructed these points, the polynomial that defines the discriminant would lead you to this very high, the c to the 6. So you have some high exponent here that's 6, and the conductor is just some constant times the radical of c. So you can already see kind of the comparing these two terms. You see that the logarithmically it's at least 6 times. So just kind of writing down the conclusion here, you can construct from this construction, you can construct you will get an infinite family where the Szpiro ratio is close to 6. So here in this construction, it's kind of artificial that we have deliberately constructed something that would give you a six power in the exponent to in the discriminant to give you this 6 as the Szpiro ratio. So it's more maybe a natural question to ask is what if we consider kind of more natural general families where it's not so obvious that we have kind of forced some high power in the discriminant. So the first family that you would think of is maybe let's just take all elliptic curves. Let's just take all elliptic curves with minimal Schwarzschild in their minimal Schwarzschild model. So you would, in some sense, you would vary A and B such that they give you a minimal Schwarzschild model, and we order these curves by their naive height. Of course, it's also natural to ask if we can order them by discriminant or by conductor, but it's usually harder to do any other ordering than the naive height. So let's just stick with the naive height for now. And in arithmetic statistics, we usually like to ask question about, well, how often does something happen? So we'll look at maybe the proportion of elliptic curves with naive height up to some bound, and we ask, well, how often does it satisfy some prescribed properties? And then we look at this behavior as this parameter n tends to infinity. So so going back to Szpiro ratio, for Szpiro ratio, there's a theorem by Fouvry Nair Tenenbaum. They show that, so if you take all these elliptic curves in minimal Schwarzschild model, whether you're ordering by discriminant or by naive height, almost all of these curves satisfy has Szpiro ratio satisfying this lying in this range here. So it's very close to 1 in some sense. So this lower bound here just comes from the trivial bound. So the content of this theorem is really on this upper bound here. So they've shown that for almost all curves, the Szpiro ratio is arbitrarily close to 1. So the exception set here depends on the epsilon, but it's something that tends to 0 as the parameter n would tend to the proportion tends to 0 as the parameter n tends to infinity. So in some way, this is claiming something that seemingly is a bit stronger than Szpiro's conjecture, but of course it's not, because you have thrown out some zero density subsets of elliptic curves, but this bound is somehow very strong just by looking at it, because Szpiro ratio only tells you an upper bound of 6 plus epsilon. But if we look at kind of what's actually happening, then maybe it's not so surprising. So let's look at let's look at some heuristics first. So if we look at the conductor, so as I said, most primes of bad reduction should be multiplicative. So the conductor should be very close to the radical, up to some constant multiple. So this is because it's more common to have multiplicative reduction than additive reduction. So yeah, we expect that the conductor is almost square free in some sense. On the other hand, the minimal discriminant up to some constant is just the value of the polynomial 4aq plus 27b squared. And this is a square-free polynomial. There's no square factor if we try to factorize it. It's square-free as a polynomial. So if the value it takes is random, then we should expect that the value is also almost square-free. So the value should be usually should be close to square-free, at least usually. So we expect that that then the radical and the polynomial and its radical should be very close to each other because you don't really have very many square factors. So we expect that that the radical of the discriminant is not too small compared to the absolute value of the discriminant. And over integers, this is a classical theorem by de Bruijn. So there, from this theorem, so from his work, we can deduce that the proportion of integers with a very small radical to be yeah. So from his work, we can deduce that almost all integers have its radical is very close to the value itself. So in some crude sense, it's saying that most integers are almost square free. So what we need here is then to kind of, instead of going through all the integers, what we're looking at is polynomial values. To be able to prove the theorem of Fouvry Nair Tenenbaum, then we need to kind of look at this distribution, this proportion, but instead of looking at overall integers, we look at polynomial values. This is just a kind of a heuristic to show you that, well, if we are picking kind of a random integer, then we expect that its radical to be very close to the integer itself. So if the polynomial has no obvious square factors, then we expect that this polynomial would kind of take a random value. Then it should also not have a very big square factor. Right. So okay. So that's heuristically why we expect that then the Szpiro ratio to be very close to 1 when the polynomial of that defines the discriminant is square free. Right. So instead of overall elliptic curves, what I looked at, as suggested by the title of my talk, special families, and these are families with prescribed torsion subgroup. And it turns out that having non-trivial torsion kind of implies that the Szpiro ratio is typically a bit bigger than 1. So what I've shown is that given fixing a torsion subgroup, say, and there are 15 possible torsion subgroup classified by Mazur's theorem. So fixing any one of these possible torsion subgroup for almost all elliptic curves with this torsion subgroup and ordering by naive height, then their Szpiro ratio is arbitrarily close to the values that are given in this table. Yeah, so in the trivial case, when G is the trivial subgroup, this is just a consequence of result of Fouvry Nair Tenenbaum, because almost all elliptic curves have non-trivial. Almost all elliptic curves have trivial torsion. So most elliptic curves would lie in this first case here, and this is this one follows from Fouvry Nair Tenenbaum. But in the other cases, when the torsion subgroup is non-trivial, then it turns out that the typical value of the Szpiro ratio is a bit larger than 1. Right. So next, I want to mention some ideas that are used in the proof and maybe suggest why the typical Szpiro ratio is a bit larger. Okay, so one thing that is helpful is that there's a result by Heron and Snowden that computed the order of magnitude of the number of curves with prescribed torsion when ordered by the naive height. So we have so what they did was so for most possible torsion subgroup G, there is a parameterization of these curves coming from modular curves, and given so fixing a G, and in most of these cases we can express the family as kind of a one-parameter family, where these so these F and G are polynomials in one variables. So instead of so we have a very nice description of these families. Usually they are some nicely parameterized families, so we can do counting on them. And it's easier to control when you have a nice parameterization. Yes, but the first problem here is that this is over the rationals, because T is a rational parameter. So we need to first make this model integral so that it's easier to work with. So what Heron and Snowden did in their paper was that they so we can write this T as a fraction A over B, where A and B are integers, and we can do a transformation to make this into an integral model. So we can multiply this term by b to the 4m and this last term by b to the 6m. That will not change the Q isomorphism class. And m is picked in a way, is an integer picked in a way such that these two polynomials are both in both have are both a polynomial in two variables. So you clear out any you clear out the denominator and turn this into an integral model, and you then you're able to write down the then we're able to write down the discriminant in terms of these two polynomials that are now also homogeneous if you've picked them correctly. Then the discriminant, just recalling, it's minus 16 for a cubed plus 27b squared. And now this a and b are just these two polynomials in the little a and little b. So you can write this discriminant as a polynomial that is now homogeneous in two variables. Then what we next need to do is that we want to show that logarithmically the radical of this polynomial d is usually very close to the absolute value of that polynomial. So that's the goal we need in order to show that in order to show that it's kind of as expected. And I guess, okay, so what I'm writing here is not okay, so it's maybe not that accurate because so just as an as an example, if we take one of the subgroups, one of the torsion subgroups, say C5, then this polynomial D would look like AB to the 5 all to the 5 times quadratic factor. So we actually don't expect that the radical is very close to the polynomial itself because of this exponent here. But we expect that each of these factors should be close to square free. So up to kind of weighting everything correctly to control to kind of take into account to this exponent 5, then we were able to we would be able to prove our theorem. And the reason that the Szpiro ratio is in this case the Szpiro ratio is close to 3. The reason that it's close to 3 is precisely because there's this high exponent here that is kind of making the radical smaller than expected. So the goal is to show that any of these irreducible factors or square-free factors are as expected. So what should really happen here is the radical of I should be saying that the radical of square-free factor of D is not too small compared to itself. Okay, and this is done by generalizing some of the techniques in the paper by Fouvry Nair Tenenbaum. So by generalizing some of their ideas, I was able to obtain a theorem that's a little bit more general. So suppose you have a polynomial with that is square free, so it has no square factors, and I need the additional kind of technical assumption that it is monic in one of the variables. And then letting pick for any nice box B, which I will not define. I can't not go into what nice means here, but one of the properties that it has to satisfy is that the sides should be bounded. Then within this box, the value of the value of the polynomial is bounded above by some constant times the radical of the polynomial to some exponent here. And this holds for almost all points in this nice box. There are some exceptions, but this exception is something that tends to zero as this box grows larger. So this K here is this kappa here is optimal when the degree of the polynomial is at most 3, and when it's when the degree is larger, this kappa is a bit worse than expected, because we expect that this exponent to be close to 1 as long as this polynomial is square free. But we're not able to achieve that when the degree is a bit larger. Okay, so right, so in kind of the last part of the talk, I will just mention a few ideas that goes into the proof. Yeah, so the main strategy is to generalize work of Fouvry Nair Tenenbaum. One observation that is key to kind of even start the proof is to observe that when the radical is small, then we should expect a large square factor of that divides the polynomial. Because if the square part of this polynomial value is small, then logarithmically this d should be very close to the f of x. So if this is not the case, then we expect that this m to be kind of large, and this d here to be kind of small. And this observation allows you to then get some saving by applying some sieve methods. So the key bound is to the key bound that goes into the proof is by kind of fixing D and then applying Gallagher's larger sieve to count the number of points X. And then we take this bound that we get from the larger sieve, and then we, at the end, sum over all possible D. Right, so this is kind of just the main idea of the proof. Right, and since I have a little bit more time, maybe I will mention also some applications that that kind of led me into thinking about the distribution of Szpiro ratios. And this is in the area of counting integral points on elliptic curves. So for minimal short Weierstrass equations, there's a conjecture by Lang that says that the number of integral points should be uniformly bounded by should be bounded by c to the rank, where this c is an absolute constant. So this c should not depend on the elliptic curve itself, as long as this this model that we're taking is minimal. And one of the results in this direction is a result of a theorem by Hindley and Silverman that shows that the number of integral points is bounded above by C to the Szpiro ratio times the rank. And the C is also an absolute constant. So it's just off by the Szpiro ratio. So if we believe in Szpiro's conjecture, then the Szpiro ratio should be bounded, and so then we should believe also in this conjecture by Lang. But it seems hard to prove that the Szpiro's ratio is bounded. So well, at least we can say that if we have that the exceptional set to Szpiro's conjecture is small, then the exceptional set to Lang's conjecture is also small. So by knowing that, well, most elliptic curves in certain families have bounded Szpiro ratio, then we can say we can deduce kind of a bound that's of C to the rank, well, at least for almost all elliptic curves in certain families. So that is just kind of one application and motivation of studying this distribution of Szpiro ratio. And that's the end of my talk. Thank you for listening.